Hi everyone, Mr. Neighbor here, and we're talking about the last bits of seismic waves, the L wave and the R wave. These stand for the Love wave and the Raleigh wave. So they are the two slowest waves. So after primary waves, P waves, come S waves. Then the next in line for speed is the L wave, and the slowest one is the R wave. Okay, so these are the two waves that cause the most damage when it comes to earthquakes with structures. So the reason being, with a love wave, you have reinforcements of buildings and their foundations going straight into the ground. However, you see this churning motion moving back and forth, and that upsets the foundation because it's not just being moved with the building, it is being churned back and forth. So that's where the structure starts to fall apart then. Raleigh waves, kind of for the same reason. You'll notice it's a combination of compression and compression and transverse waves, where you have the squeezing happening, but also this hump happening. And when the structure, the foundation of the building is perpendicular to the surface, it's going to be squeezed by those compression waves as well as moved. So that's the problem that's happening, and that's why they're causing the most damage, these surface type waves. So these are the two surface waves. Before we had the transverse wave and we had the longitudinal compression wave. But these are the most dangerous, the most destructive, because they are surface waves. It's because they have that rolling chaotic movement. And L waves, they're the ones that can't affect water. So you might see it on the edge of a pond, but you won't see it go through it. So it couldn't go through the core of the earth either. Raleigh waves, though, they can affect major bodies of water. So Raleigh waves can. L waves, love waves cannot. The last part of this video, I want to talk about earthquakes and how to calculate some things with earthquakes. So earthquakes are measured with seismographs, and they record and measure P and S waves. So the first two waves that are going to be coming from the earthquake. So the time between the start of the P wave and the start of the S wave help us to determine where the epicenter of the earthquake is. So when we look at one of these, the very first line you see, that is where the P wave starts. Then it tapers off. The next huge jump that you're going to see, that's going to be the S wave. So if we look at this time in between here, that can help us determine the distance it is away from whatever center we're at that's reading this seismograph. So the next slide is going to show us a little bit more with that. So once you have your time is key. We're going to use that in a time distance graph. Notice I didn't say a distance time graph. Normally we have time down here on the x-axis and distance on the y-axis. This is backwards. We're going to use the time as something that we get out to determine the distance. So one way that we can use this earthquake P wave, S wave travel time graph is to take the time in between them. So let's say our time in between the P wave and the S wave was 4 minutes. We take this. Normally, we would take a piece of paper and mark the beginning and the end, and we kind of drag that piece of paper along until we eventually see where it matches up with the S and P wave. So I think right here, 2, 3, about right here, probably a little bit further in, and we look down and we see that is a distance of 3 times 10 to the third kilometers. Okay, so 3 times 10 to the third kilometers, that would be 3,000 kilometers away. So now we know where exactly the earthquake, or we don't know where exactly it happened at, but we know that it is 3,000 kilometers away from us in this big circle away from us. So we don't know where it happened. But if we have two other centers that also recorded these P and S waves, they will have different distances. Maybe theirs is only 2,000 kilometers away, and a different one yet is 5,000 kilometers away. Where those three spots intersect, that is the epicenter of the earthquake, and we can find where it's at. And then we can send out alerts and things to make sure people get to safety. Now, before we move to the next slide, I do want to just point out this graph has been made up of many calculations, and now it's just used by people to do rough calculations for distances to the epicenter. Roughly, if you want an equation to do that, you can take your time that you found before, the time between the P and the S wave, in seconds, not minutes, because when we do calculations in physics, you should be using seconds. If you times that by 13 and minus 330, that will give you your distance in kilometers. Sorry, your distance in meters, I believe. Might have to check that one. So I'll look at that, but I'm thinking it's going to give you out a distance in kilometers, which it should give you out a distance of meters if we were talking true physics calculation, because distance is meters. But I'll look into that one. We'll be using this graph more often than not. So here's just a visual of our distance that we found that the earthquake could be in. Here's another location in Elko. They found it to be 702 kilometers away. And then this in Eureka found it to be 478 kilometers away. And where they all intersect, that is where the epicenter is. So right there, that's where the earthquake, the fault line occurred and shifted. So what we just calculated was the epicenter, the location of the earthquake. From that, we can now calculate the magnitude of the earthquake. And we do that using a Richter nonogram. So the Richter nonogram is just a representation of a couple pieces of data and how they're related. On one side, you have the distance in kilometers. So that's what we found using that graph before. You have the amplitude, and the amplitude is the amplitude of the S wave. So if we look at the seismograph, we have the center line running right through there. This right here is the amplitude. So it looks like this amplitude is around 270 millimeters. So we would look for 270 on here, and then we would connect the dot from our amplitude to our distance dot, whatever we found that to be, draw a line to it using a straight edge, and we would do that with our other seismograph readings too from the other locations on the country. And where all of those meet, that will tell you what the magnitude of the earthquake is on the Richter scale, how powerful that earthquake is. So where they all cross is where you'll find the magnitude, but it requires the distance and the amplitude.